For week 7, we'll be exploring sampling distributions and large sample confidence intervals for mu. In this first part, we'll just focus on sampling distributions. This is section 4.8 and 4.9 in your textbook. So where we're going and where we've been. In the last few sections, we learned how to calculate things like the probability that x is less than 2.5, for example, or maybe x is between certain numbers. And that's great, but what happens if we're interested in the probability that a sample average is less than a number, or greater than a number, or maybe between numbers? So notice the difference here is that here I have just x, and here I have x bar, the sample mean. Well, in order to actually understand what's going on with the sample mean, we need to know what the distribution of sample means look like, and that's what we're going to be doing. All right, so let's talk about what this whole sampling distribution is. So, like when we start off, we have a population of individual x values. This is just our traditional population. I show a circle here, and in this circle includes everyone in the population, every single x value in the whole population. So theoretically, what we can do is, and this is completely theoretically, we can't really do this in practice, is when we take a sample, what we do is we just randomly pick some people from the population or some things from this population. And in this example, let's say we have a sample size of 50, and maybe our average was something like 2.86. So what I'm going to do is I'm going to take these random 50 people. I found the average of those people was 2.86, and I'm going to record it. So I'm going to take that sample average and put it in what's ultimately going to be what's called a sampling distribution. So that's my first one. Now theoretically, in practice I only do one sample, but theoretically I could do really an infinite number of samples. I could sample another group or another group or another group. I could pick even the same person more than once. So theoretically I can take a whole bunch of samples, all of size 50. But even though all the samples were randomly taken from the same population, they all have the same sample size, most of them are going to have different sample means. And that just happens. So maybe for this sample, the sample mean might have been something like 2.73. So I'm going to record that sample mean. And there you go. So again, I can do this an infinite number of times. You can take an infinite number of samples from the population, theoretically. So there we go. We have a whole bunch of x bars. Most of these will have completely different values. But most of them will probably be pretty close to the actual population average if you think about it. Okay, so what we want to do is instead of looking at this distribution from the population, which could look like, anything really, we want to look at this distribution of x bars instead, and that's going to be called the sampling distribution. So just to kind of go over some symbols. So before, when we talked about our distribution of x values, just our population distribution or frequency distribution, we called the average of this distribution mu. Alternatively, you might have noticed in your calculator that they might call it like mu x or something like that to indicate that this is coming from x values. Standard deviation, we called it sigma, but you can call it instead sigma subscript x to indicate that, again, it's the standard deviation of x values. I would always prefer using mu or sigma instead to prevent confusion, but it isn't uncommon for you to write the subscript x. So similarly, to indicate that we're talking about the average of the sampling distribution of x bars, or the standard deviation of the sampling distribution of x bars, we'll use that subscript notation, and instead of x, we're going to use x bar instead. So the average of our sampling distribution will be mu subscript x bar, since it's the average of the sampling distribution of x bars, and the standard deviation will be sigma x bar. Okay, so some characteristics of the sampling distribution. The sampling distribution will have the same mean and the same population as the x values, but a smaller standard deviation. Well, let's talk about why for a moment. So going back, looking at what's going on with our sampling distribution. In this example, I was picturing maybe taking samples from a population of HCC students. The average for this population might be something like 2.8. So in other words, the average GPA of all HCC students might be somewhere around 2.8. But when I do a sample, some people in the sample might have a pretty low GPA, like 1.2, and some people in the sample might even have like a 3.9 or a 4.0, because GPAs vary all over the place. But if I average 50 GPAs from randomly taken from a population and into a sample, I would expect my sample average to be fairly close to the population average. So in this case, I got 2.86. And if theoretically I were to do it again, I might get 2.73. Maybe another time I might get exactly 2.8, or maybe I might get 2.83, or all different values. But all these values should be pretty close to the population average. And if you think about it, if I were to average these averages, it really should be the population average. Think about it. If you were to do like 50 samples from the population, all of the same size, if you were to average those averages, it should be pretty close to the actual average. I know that sounded like a mouthful. All right, so going back to what we just discussed, specifically, we expect that the mean or the average of the sampling distribution of sample averages to be the population average. If you average a bunch of sample X bars, you'd expect to get the population average. The standard deviation we expect to be smaller because if you're looking at a sample of 50 students, you would be very, very shocked to find that the average GPA of those 50 students was something like 1.5, even though it wouldn't be so unusual to find a single student with a GPA of 1.5. So because we expect the sample averages to be so close to the actual population average, the standard deviation of that distribution is going to have to be smaller. And specifically, it's going to have to be sigma over the square root of n. This formula is derived it's not too complicated of math, but it's a little beyond the scope of this class. You need to be very comfortable with summations in order to do this. So maybe if you take pre-calculus after that, you could derive this formula. Anyway, so to prevent some confusion, instead of talking about the standard deviation of sample means, because when we say standard deviation, normally we mean just the sigma, people often refer to the sigma x bar instead as standard error, or the standard error of the means. But if I say standard error, I'm specifically referring to sigma x bar. All right, so the shape of the sampling distribution. There's going to be three cases we're going to explore. The first case is suppose that your starting population has a normal distribution. If your starting population looks like a normal distribution, then the sampling distribution will be normal as well. Case 2, which is the more interesting case, if your starting population has some unknown distribution or a distribution that we know is not normal, but the idea is we don't know if this distribution is normal or not, and if your sample size is large, then we know the sampling distribution will be normal. In other words, your population can look like whatever, but as long as you take a large sample, your sampling distribution of X bars will be normal, which is good because we know what a normal distribution looks like. So first question is, well, how large is large? And there's really no great answer to this. Like I might think, an elephant is large, but an elephant isn't large compared to like a huge whale. So large is really an arbitrary term, but just to kind of be a little bit more precise, we'll say that in this class that if n is greater than or equal to 30, it's a large sample. And it's not just, a lot of people use this cutoff, but it really is an arbitrary cutoff. So in reality, the idea is that the larger your sample size, the more normal that sampling distribution of X bars becomes. So in other words, a sample size of even 10 might look fairly normal. All right, case 3. If your starting population of X values has some unknown distribution and we have a small sample, then unfortunately we don't really know anything about the shape of the sampling distribution of X bar. That doesn't mean that you can't do anything, but we won't be able to use the techniques from Chapter 5 and Chapter 6, our inferential statistics techniques that we're going to learn in there. There are other things you can do. There's something called non-parametric statistics, but that's beyond the scope of this class. But don't worry, it's not like statisticians can't work with small samples. You can. You just have to do a little bit more involved analysis. All right, just to kind of summarize what we were saying. So if we start off with a normal distribution, like this little purple distribution down here, then even if we have a sample size of 2, it's still going to be normal. And if we have a sample size of 3, again, the sampling distributions, or 5 rather, the sampling distribution is still going to be normal. And if we have a sample size as large as 30, it's still going to be normal. It's just going to have a smaller standard deviation. All right, but these other cases are the more interesting ones, because in these, the original population of X values didn't look normal at all. And notice how I labeled these axes here, X, 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 to indicate that this is just the original population. But when we look at the sampling distribution of X bar, they start taking on kind of a more normal shape. Like we start off here with this uniform distribution. Just looking at a sample size of 2, it starts turning into a triangular distribution, the sampling distribution of X bar does, rather. By a sample size of 5, it looks really like a normal distribution. And by a sample size of 30, it's definitely, undistinguishable from a normal distribution. And the standard deviation is much smaller. All right, so the idea is that no matter what the original population looks like, as long as we take a large enough sample size, your sampling distribution of X bars is going to be normal. All right, so this is a very important theorem in statistics. It's going to guide everything we do in Chapter 5 and Chapter 6, actually. All of the inferential statistics we're going to learn in this class. So because it's such an important theorem, it has its own name. It's called the Central Limit Theorem. And just to summarize it, the idea is that if we take a random sample of a certain size and observations from any population with a mean of mu and standard deviation of sigma, then when n gets sufficiently large, and we'll say n greater than or equal to 30 for this class, the sampling distributions of X bars will be approximately normal, with a mean of mu X bar and a standard deviation of sigma over square root of n. I apologize, I try to draw this with a mouse, so it doesn't look quite normal. It looks kind of choppy, but the idea is we can start off with some crazy distribution of X values, but our sampling distribution of X bars will be fairly normal with a smaller standard deviation, less spread out. And notice again here, I labeled it X bars to indicate we're talking about a sampling distribution of X bars. All right, so we can use this idea that the sampling distribution of X bars is going to be normal with a mean of mu and a standard deviation of sigma over square root of n to analyze certain problems. So let's just do one example. And if you find this one example a little confusing, don't worry too much. We'll go about how to do this a little bit in a more formal manner in Chapter 6. But let's just start off by, practicing. All right, so in this example, an ice cream producer claims that the average weight of their ice cream cartons is 12 ounces, with a standard deviation of ½ an ounce. So I'm not sure if I believe this. I think they might be cheating their customers. So to investigate this, I decide to purchase 100 ice cream cartons and weigh them. The average weight of my sample is 11.87 ounces. So the question is, should I believe the manufacturer? So first off, notice let's pick out the important symbols. And let me get my marker out. Let's use purple. All right, so here we see that the manufacturer claims the average weight is 12 ounces. So this is what the manufacturer is claiming mu is. We don't really know if that's true, but that's what they're claiming. Here we see the standard deviation is ½ an ounce. So again, that's what the manufacturer is claiming sigma is. Okay, so I purchased 100 cartons. So this 100 over here is my sample size, my n. And the average weight of those 100 cartons is 11.87 ounces. Now, being that this is the average weight of my sample, we're going to use the symbol X bar. And remember, this one sample I took is one of an infinite number of samples I could have taken. So our X bar is just one value out of many that could have happened. All right, so just to draw out what happened, since our sample size is 100, where did my mouse go? Okay, since our sample size is 100, Well, n is definitely greater than or equal to 30. So in other words, we know our sampling distribution is going to be normal, or approximately normal. So I know my sampling distribution is going to be normal. Okay, and again, these are x bar values. Now I know the average x bar, mu x bar, is going to be equal to mu. I know that fact, so I know mu x bar is equal to mu, and according to the manufacturer, mu is just 12 ounces. All right, I also know, since I'm up here writing, sigma x bar is supposed to be sigma divided by the square root of n. Now, if the manufacturer is telling the truth, sigma should be equal to 0.5, and n is 100. So I just do 0.5 divided by the square root of 100. Well, the square root of 100 is just 10, and 0.5 divided by 10 is just 0.05. All right, so that's sigma x bar. And the average of this distribution should be 12, if the manufacturer is telling the truth. So if the manufacturer is telling the truth, then I just got unlucky, and my average of my sample was 11.87. That is my specific x bar value. I need to figure out if this is unusual or not. And to figure out if this is unusual or not, we could look at maybe the z-score associated with it. Or alternatively, I would still want to find the z-score, but I could find out what's the probability that I actually wind up with the sample mean I got, or even more extreme. Because if this number is really small, then it was very unlikely for me to find the sample mean that I found, which means that either I got very unlucky or the manufacturer is lying. So let's figure out how unusual getting less than 11.87 ounces is. All right, so we know z-scores are always centered around 0, so that was easy. But I need to find this z-score here for 11.87. Well, remember our z-score from before was equal to x minus mu over sigma? That's not going to work this time because we don't have x values, we have x bar values. So really I want to do x bar minus the average x bar divided by the standard deviation of the x bars. Well, okay, so my x bar is 11.87. The average x bar, if the manufacturer is telling the truth, is 12. And the standard deviation of the x bars, again, if the manufacturer is telling the truth, is 0.05. Okay, so this would be negative 0.13 divided by 0.05, which is, I believe, negative 2.60. So let me put that down there. Okay, I just took out a calculator to check it, and yes, it's negative 2.60. All right, so we need to find this probability here, and we can do that using the table. Remember, though, the table gives us the probability of z being between 0 and some number. So we can look on the table to find the probability that z is between 0 and positive 2.6, which is going to be the same as this probability between 0 and negative 2.6. So let's find that. All right, so let's see, 2.6, where's my cursor? Let's see, 2.6 is over here. Here's that second decimal place, the 0 is over here. So this is the number we wanted to look at, this 0.4953. Okay, so this probability here is 0.4953. And since we know the whole area to the left of 0 is 0.5, 0.5 minus 0.4953 is 0.0047. That's our answer. The probability that x bar is less than or equal to 11.87 is 0.0047. In other words, there's only, if I move the decimal place over 2 spots, there's only a 0.47% chance of this happening. You know, less than 0.5%. This is very unlikely, right? Less than 0.5% chance for us to find the sample mean we found if the manufacturer is telling the truth, which means no, I do not believe the manufacturer. No, I do not believe the manufacturer. Or I just got very, very unlucky.